So continuation of the lecture number 2. Here we give some special type of relation, some relation naming as reflexive, symmetric, transitive, and so on. We started with definition. Reflexive relation. What is the meaning of reflexive relation? Let A be a set and let R be a relation on A, then R is called the reflexive if this symbol is known as for all A belongs to capital A rho A holds. That means if you can define a relation over a A, this relation becomes reflexive relation if it's happen for every element. It's very important, for every element A rho A satisfied. That means if we consider a set A, just to make a cross product A cross A, then we find a subset of the Cartesian product A cross A, that should be the relation. And this Cartesian product, if it's happen, every element pair is every element itself occur in the relation. That means A, B, B, C, C, D, D, E, E, and so on. In that case, we say the relation is a reflexive relation. According to the previous example, if we consider this diagram, okay, if we consider this diagram, this diagram represents the relation A. This relation is nothing but this A, B, 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 C, C, B, A, B, D, and C, D. And the question is that is this relation is a reflexive relation or not? Yes or no? That is very important. If in every vertex, if we consider a element of the set is a vertex in the diagram, then if every vertex has a self loop, if we consider the arrow diagram, every vertex has a self loop, then we say that the relation is a reflexive relation. From the diagrammatical representation, you can say a relation is a reflexive relation if it's happened again we repeat, every vertex has a self loop. Every vertex has a self loop. So now we move to the second case, symmetric relation. Let A be a set and let R be a relation on A, then R is called symmetric if for all A comma B belongs to A, whenever A or B holds, if it is happen that A rho B holds, then if it must be B rho A also hold, then we say that the relation is a symmetric relation. So how can I clear the concept a relation is a symmetric relation or not? According to the same diagram, if we move to the same diagram, this one, it's represent A rho B holds, then B rho A also hits. That doesn't mean the relation is a symmetric relation, because here we can also observe that B is rho related to D. The definition says if B is rho related to D, then this relation is said to be a symmetric relation if it happens that D is rho related to B also. So here B is rho related to D, but D is not rho related to B because there isn't any arrow from D to B. So this relation, according to this example, this relation should not be a symmetric relation. Okay, you can say a relation is a symmetric relation in a diagram. It is happen that every row has an opposite direction arrow. every arrow there has an opposite direction arrow. If B row C, then if there isn't C row B, then it should be a symmetric relation. B to D, then there must have a arrow from D to B. The next relation is the transitive relation. Transitive relation. What is transitive relation? Let A be a set and let R be a relation on A. Then R is called the transitive if for all A comma B comma C belongs to A whenever A R B and A R C hold, both are hold. If both are hold, then A row C must hold. Then A row C must hold. I just give a real life example for a transitive relation. If Ram is a friend of Sam, Sam is a friend of Modhu, then if it is happen that Ram is also a friend of Modhu, then we say that the friend relation is a transitive relation. It may be happen that Modhu should not be a friend of Ram. In that case, this relation should not be a transitive relation. Ram is still is a friend of Modhu. Modhu is friend of Jodu, but Ram is not a friend of Jodu. In that case, this relation should not be a transitive relation. Okay. So, brother relation is a global example of a transitive relation. A is a brother of B, B is a brother of C, then A should be a brother of C. So, brother is a transitive relation. And brother is also example of a symmetric relation. A is a brother of B, B should be a brother of A, therefore it should be a symmetric relation. But it's not the example of reflexive relation. A man is not a brother of itself, so it should not be a reflexive relation. It may be happen that a relation is reflexive but not symmetric, not transitive. It may be happen that a relation is symmetric but not reflexive, not transitive. It may be happen that the relation is a transitive but it's not a symmetric, not a transitive. That's totally depend upon the different example. It may be happen that all the three relations should holds. If it is happen that all the three relation hold, then this relation is called the equivalence relation. Okay, then this relation is called the equivalence relation. Then the relation is called the equivalence relation. A relation R on a set A is called an equivalence relation, also known as RST. Why it is represented RST? R for reflexive, S for symmetric, and T for transitive. So it is known as the reflexive symmetric transitive or a equivalence relation if R is reflexive, symmetric, and transitive. If a relation satisfy these three norms, reflexive, symmetric, and transitive, then this relation is known as the equivalence relation. Another very important relation is anti-symmetric relation. Anti-symmetric relation, it's a very good example. It may be happen that some relation is a anti-symmetric relation. What is this? A relation R on a set S is called a antisymmetric if for all A comma B belongs to S. Sorry, A row B and B row A both are hold. We just consider A row B and B row A both are hold. If only happen that if A equals to B, then we say that the relation is an antisymmetric relation. You have some confusion about the symmetric and antisymmetric or the other definition. So here we clear your concept using a verbal example. Say if we consider a relation divisibility. Okay, 2 divides minus 2. So 2 R minus 2, R represent the relation, or row, sometimes it's represented by row, 2 row minus 2, satisfied. Again minus 2 is divide 2, therefore minus 2 is also divide 2. In that case we say that a row 2 row minus 2 as well as minus 2 row 2 both are satisfied, but it should not happen that it is a equals to b because 2 is not equals to minus 2. So in that case we say that this relation is a symmetric relation, which is not the antisymmetric relation. Okay, so happy learning up to these three lectures, and still waiting for the next lecture for continuation of the number theory relation. Thank you.